Hello students, in today's video presentation we will study about the potential energy of a spring, which is an example of variable force and conservative. This is given as section 6.9 in the chapter number 6 of physics for class 11. We will also study about the various forms of energy and law of conservation of energy. In the previous sections, we have discussed mechanical energy. We have seen that it can be classified into two distinct categories. One based on motion, namely kinetic energy, and the other on configuration or position, namely potential energy. These energies come in many forms which transform into one another in ways which may not be often clear to us. But after studying this, these concepts will be clear. So I welcome you once again. Please note down all the important points. The potential energy of a spring. The potential energy of a spring can very well be understood by analyzing the figure given on the screen. Here three figures are shown. The first figure, figure A, shows a block attached to a spring and resting on a smooth horizontal surface. The other end of the spring is fixed, is attached to a rigid wall. The spring is lightweight and may be treated as massless. In an ideal situation, the spring force Fs is proportional to x, that is Fs is proportional to x, and where x is the displacement of the block and block displacement of the block from the equilibrium position. The equilibrium position is when x is equal to 0. The displacement could either be positive as shown in figure B, this is the positive x, or it can be negative as shown in figure C. So positive x is positive when spring is stretched and x is negative when the spring is compressed. This force law given in the previous point is called Hooke's law and is mathematically stated as Fs is equal to minus k into x. Let it be equation 1. The constant here, k, is called spring constant and its unit is newtons per meter. The spring is said to be stiff if the value of k is large, and the spring is soft if the value of k is small. Now we will consider some special cases. Case number 1, stretched spring. As shown in figure B, that is the middle figure, when the block is pulled outwards, the extension is xm. This x is xm. The work done by the spring force is given by the relation Ws, work done, Ws is equal to work done by spring equals integral 0 to xm Fs into x, or Ws is equal to minus of kx into dx. Here we have put Fs is equal to minus kx as per the equation 1. So now integrating and simplifying, we get Ws is equal to minus of k into xm square by 2, because integral x dx is x square by 2 and the upper value is xm. Lower value is 0. So 0 means the lower term is 0, upper term is kxm square 2. The work done is negative because Fs and Xm are opposite in direction. Hence, the work done in this case, the Fs, the work done by spring is negative, whereas the work done by the external force is positive. This figure B can also be explained using a diagram D, which is shown on the right hand side. The plot of Fs versus X is shown in figure D. The area of triangle, shaded triangle, that is shaded triangle OBAO, represents the work done by the spring force. This is the work done by the spring force. Due to the opposing sign of Fs and X, this work done is negative. Here, the Ws is equal to minus K into Xm square by 2 as shown in the figure. Now we will take up the case of a compressed spring that is shown in figure C. So here X is negative because X is on the left hand side. This is when it is compressed, X is negative. The work done by the spring force in this case also is Ws is equal to minus of K into Xc square by 2 as explained earlier. Let it be equation 3. If the block is moved from xi to xf, in yet another case 3, if the block is moved from xi to xf, Ws is given by the integral minus of integral xi into xf of k into x into dx. This also is explained earlier. Only limit here in this case number 3 is xi to xf, where xi is the initial position and xf is the final position. Therefore, simplifying and putting the limits and integrating, we get Ws is equal to kx I square by 2 minus kxf square by 2. Let it be equation 4. Now we will take some special cases. If in equation 4, if xi is equal to xf, then work done is 0 because the two terms on the right hand side of equation 4 get cancelled with one another. Hence, the work done by the spring force depends only on the end point. Thus, the spring force is a conserved force. Now, we will recapitulate the relationship for potential energy. When the spring is compressed or elongated by x, displacement x, then potential energy is stored in it. Therefore, potential energy equals of the spring equals V, capital V is equal to half of K into X square. Since the spring force is conservative, the total work done by the spring in a cyclic process is 0. Therefore, kinetic energy equals potential energy. And the maximum speed of spring of the block Vm is given by equating potential energy with the kinetic energy. Potential energy as per this equation 5 is half of K into Xm square equals kinetic energy half of M into Vm square. Therefore, Vm becomes rearranging and simplifying, we get Vm is equal to square root of K divided by M into Xm, where Xm is the amplitude of the block. In the spring block system, which was shown in the previous slide, the kinetic energy gets converted to a potential energy and vice versa. However, the total mechanical energy remains constant. Please see the figure on the right hand side, which shows the parabolic plots of potential energy V and kinetic energy K of a block attached to a spring obeying Hooke's law. The two plots are complementary, one decreasing and the other increases. See, when this blue colored graph is a potential energy K. So when K increases, V, that is potential energy, V decreases. This black colored is V and blue colored is K. So but at any instant of time, E is equal to K plus V. That means the total mechanical energy E is equal to K plus V. If the two forces acting on a body are conservative, Fc, and non-conservative, Fnc, then by work energy theorem we have Fc plus Fnc into delta x is equal to delta k. But we know Fc into delta x is equal to minus delta v. Therefore, substituting the value of Fc into delta x is equal to delta v and rearranging, we get delta k plus delta v equals Fc into delta x. Therefore, k plus v is E. Therefore, delta E is equal to Fnc. Where E is the total mechanical energy and over a path, this assumes the form EF minus EI is equal to WNC, where NC is the total work done by the non-conservative force over the path and depends on the particular path. Now we will summarize some remarks on conservative forces. Information on time is absent from the above discussions. In the example considered above, we can calculate the compression, but not the time over which the compression occurs. There is no time factor. A solution of Newton's second law for the system is required for temporal information. Not all the forces are conservative. For example, friction is a non-conservative force. The zero of the potential energy is arbitrary. It is set according to the convenience. For the spring force, we took V of x is equal to 0 at x is equal to 0. That is, we had shown the diagram A in the previous slide. Vx is equal to 0 at x equal to 0. That is, unstretched spring had 0 potential energy. For the constant gravitational force mg, we took V is equal to 0 on the Earth surface. So for all practical purposes, we take the mg constant gravitational force mg, V equals 0 on the surface of the Earth. Potential energy of a spring. Now we will understand about the concepts of potential energy by taking some worked example. Question number 8. To simulate car accidents, auto manufacturers study the collision of moving cars with mounted springs of different spring constant. Consider a typical simulation of a car of mass 1000 kgs moving with a speed of 18 kilometers on a smooth road and colliding with a horizontally mounted spring of spring constant small k is equal to 6.25 into 10 to the power of 3 newtons per meter. What is the maximum compression of the spring? Answer. At maximum compression, kinetic energy is equal to potential energy of the spring. We know K is given by kinetic energy is given by half into mass into V square, velocity square. So that is equal to half into mass is 1000 kg. It is given into V is given as, that is speed is given as 18 kilometers per hour, but when we convert it into meters per second, it is 5 meters per second. Please note 36 kilometers per hour is equal to 10 meters per second, or in the given problem it is 18 kilometers per hour is the given speed. Therefore, that becomes 5 meters per second. So K is equal to half into 10,000, 10 to the power of 3, 1000 kg into 5 square. That is equal to 1.25 into 10 to the power of 4 joules. At maximum compression, Xm, the potential energy V of the spring is equal to kinetic energy K of the moving car from the principle of conservation of mechanical energy. Therefore, potential energy V is equal to half into K into Xm square. That is equal to 1.25 into 10 to the power of minus 4 joules. Therefore, from this we can calculate Xm is equal to square root of 2 into this 2 into 1.25 into 10 to the power of 4 cross multiplying divided by K. K is given 6.25 into 10 to the power of 3. That is equal to 2 meters. Now we'll take up next question. Consider example of question number 8, taking the coefficient of mu to be 0.5, calculate the maximum compression of the spring. In this question, it is given that the coefficient of friction mu equals 0.5 and we have to calculate the maximum compression. Therefore, it is given that from the previous question, g is equal to 10 meters per second and mu is equal to 0.5 and v, the speed is equal to 18 kilometers per hour, that is equal to 5 meters per second. Therefore, in presence of friction, both spring force and frictional force act so as to oppose the compression of the spring as shown in the figure. See the figure here. There is a spring attached to the motor which is on wheels and its frictional force is opposing the motion. The motion, because of compression, the motion is this direction, friction is in opposite direction, mu into m into g. So in presence of friction, both spring force and the frictional force act so as to oppose the compression of the spring as shown in the figure. Therefore, change in kinetic energy is equal to delta K is equal to Kf minus Ki. That is equal to Kf is 0 and minus Ki. Ki is minus of half mv square. Therefore, the work done by net force W is equal to minus half K into Xm square minus mu m into g. Equating, we get half mv square is equal to minus half k into xm square minus the mu m into g of x, because work done is kinetic energy, half mv square. Therefore, mu into mg is equal to, substituting 0.5 into 10 to the power of 3 into 10, that is equal to 5 into 10 to the power of 3 newtons. Now rearranging, putting the value of mu mg in this equation, we get k into xm square plus 2 into mu m into g into xm minus mv square. This is the simultaneous equation of second order. Simultaneous equation and second order equation. We have to find the value of xm by solving this simultaneous equation. Therefore, applying the formula, x is equal to minus b plus or minus b square minus 4ac divided by 2a, where the equation form is ax square plus bx plus c, and we are taking in this case positive square root of, that is, we are taking, instead of plus or minus, we are taking only the positive value of square root of b square minus 4ac. Therefore, xm is equal to minus of mu mg plus square root of mu square m square g square plus m into k into v square divided by k, that is equal to 1.35 meters. Now we will go to next section, that is section 6.10. Here we will just glance through various forms of energy, that is the law of conservation of energy. In the previous sections, we have studied about the mechanical energy and seen that it can be classified into two distinct categories, one based on motion and the other, that is namely on motion kinetic energy, and the on the configuration, that is position, namely the potential energy. Energy comes in many forms which transform into one another in ways which may not be often clear to us. Heat energy. Heat is a form of energy. A block moving on table experiences friction, which results in heat energy. Due to friction, the temperature between the two bodies increases. The work done by friction by two bodies is transferred as heat energy. This raises the internal energy of the bodies in contact. The internal energy is associated with the motion of molecules. So the frictional force is not a conservative force, but some work is associated with the force of friction. In winter, we rub our hands, we feel warm and generate the heat by vigorously rubbing our palms together. And another example is, if you heat 1 kg of water, it releases about 42,000 joules of energy when it cools by 10 degrees centigrade. The next form of energy is electrical energy. The flow of current causes the bulbs to glow, fans to rotate, and bells to ring. Similarly, electrical energy is responsible for rotation of motors, pumps, etc. Energy is associated with electric current. An urban Indian household consumes about 200 joules of energy per second on an average. We'll study about the electrical energy in the next year, that is class 12. Chemical energy. Chemical energy arises from the fact that molecules participating in chemical reaction have different binding energies. A stable chemical compound has less energy than a separated part. So, when a compound undergoes chemical reaction, then it produces a lot of chemical energy. A chemical reaction is basically rearrangement of atoms. Chemical energy is associated with the forces that give rise to stability of substances. These forces bind atoms into molecules and molecules into polymer, polymeric chains, etc. The chemical energy arising from the combustion of coal, cooking gas, wood, and petroleum is very common in our daily life. In the next part is section 6.10.0, where we study about basics of nuclear reaction. Albert Einstein showed that the mass and energy are equivalent and are related by relation E is equal to mc square, where c, the speed of light in vacuum, is approximately 3 into 10 to the power of 8. That is, in the equation E is equal to mc square, E is the energy, m is the mass, and c is the velocity of light. So, left part is energy and right part is mass and velocity. Hence, energy can be converted into mass and mass can be converted into energy. Thus, a staggering amount of energy is associated with a mere kilogram of matter. That is, E is equal to, if 1 kg of mass is considered, E is equal to 1 into 3 into 10 to the power of 8 whole square joules. That is equal to 9 into 10 to the power of 16 joules. This is equivalent to an annual electrical output of a large 3000 megawatt power generating station. Nuclear energy. The fission and fusion bombs and life-nourishing energy output of the sun are manifestations of equivalence of mass and energy. In this case, effectively, 4 light hydrogen nuclei fuse together to form a helium nucleus whose mass is less than the sum of the masses of reactants. This mass difference, called the mass defect, delta M, is the source of energy. That means in a nuclear reaction, when 4 light hydrogen nuclei fuse to form helium, a mass defect is produced, which is the source of energy. That was fusion. In fission, a heavy nucleus like uranium U-23592 is split by a neutron into lighter nuclei. This mass difference translates into energy, which can be trapped to provide electrical energy, as in the nuclear plants. Controlled nuclear fission. If the fission process is controlled, it is a nuclear generating station or power plant. Or If it is not controlled, that is uncontrolled, it is used for making nuclear weapons. 6.10.6 The principle of conservation of energy. The total mechanical energy of the system is conserved if the forces doing the work on it are conservative. If some forces involved are non-conservative, part of the mechanical energy may get transformed into other forms such as heat, light, and sound. However, the total energy of the isolated system does not change as long as it accounts for all forms of energy. Energy can neither be created nor destroyed. Since the universe as a whole may be viewed as an isolated system, the total energy of the universe is constant. If one part of the universe loses energy, another part must gain an equal amount of energy. The principle of conservation of energy cannot be proved. However, no violation of this principle has been observed. The concept of conservation and transformation of energy into various forms like links together various branches of physics. I will read once again. The concept of conservation and transformation of energy into various forms links together various branches of physics, chemistry, and life sciences. It provides a uniform, enduring element in our scientific pursuits. Table 6.10 shows approximate energy of various phenomena that we encounter in our studies. The first item is a Big Bang, which is given in column number 1, which describes the phenomena. Column number 2 gives the energy in joules. The first item is Big Bang. The Big Bang theory is prevailing cosmological model explaining the existence of the observable universe from the earliest known periods through its subsequent large-scale evolution. It has an energy of 10 to the power of 68 joules. Radio energy by galaxy during lifetime is 10 to the power of 55 joules. Rotational energy of Milky Way is 10 to the power of 52 joules. Energy released in supernova explosion is 10 to the power of 44 joules. A supernova is a powerful and luminous stellar explosion. This transient astronomical event occurs during the last evolutionary stages of a massive star or when a white dwarf is triggered into a runaway nuclear fusion. Ocean's hydrogen in fusion is 10 to the power of 34 joules. Similarly, various other items are given, including smaller energy phenomena like turning this page. Even when you turn one page of a book, the energy involved is 10 to the power of minus 3 joules. That is of very small values. Flea hop. Flea hop has an energy of 10 to the power of minus 7 joules. A flea hop is a small flea beetle, sometimes injurious to hops. It has energy of 10 to the power of minus 7 joules. The discharge of a single neuron gives energy of 10 to the power of minus 10. Similarly, so many, like energy to break one bond in DNA is 10 to the power of minus 20 joules. So you please go through just for your information, and you need not remember all, and some important things you can recollect and note down. Next we will take up a worked example. Question number 10, which is express item number A is the energy required to break one bond in DNA in electron volts. Part B is the kinetic energy of an air molecule, which is 10 to the power of minus 21 joules. That is, air molecule has an energy of 10 to the power of minus 21 joules. We have to express it in electron volts. And part C is the daily intake of human adult in kilocalories. So some of the data is not given in the problem. We have to refer table number 6.10. So let us answer it. Energy required to break one bond. It is given, we know that it is given as 10 to the power of minus 20 in the previous table. That is table number 6.10. So that to convert it into electron volts, we should divide it by 1.6 into 10 to the power of minus 19 joules per electron volt. So that becomes approximately equal to 0.06 electron volts. The question part B is kinetic energy of an air molecule. We have to calculate in electron volts. It is given that energy of an air molecule is 10 to the power of minus 21 joules. So to convert it into electron volts, we have to divide it by 1.6 into 10 to the power of minus 19. Substituting as shown, we get value as 0.0062 electron volts. We can even express it in terms of millivolts by multiplying this value, that is 0.0062 into 10 to the power of minus 3, there where we will get in value in millivolts. Part C, the daily food intake of human adult, that is equal to 10 to the power of human adult intake is 10 to the power of 7, which is given in the previous table, divided by 4.2 into 10 to the power of 3 joules per calorie. So to convert it into calories, we have to use the factor division factor 4.2 into 10 to the power of 3. There we get 2400 kilocalories. With this, we come to the conclusion of our discussions on law of conservation of energy. In the next lecture, we will take up power and collisions of chapter number 6 of physics for class 11. Till then, goodbye.